In this video, we're going to prove a theorem about primitive polynomials. So recall that a polynomial in Z adjoint x is primitive if the GCD of all of its integer coefficients is 1. That's what it means to be primitive. And this theorem says if f of x and g of x are both primitive, then their product, f of x times g of x, let's make that a little bit clearer, the product is primitive. All right, so this may seem intuitive at first glance. It may seem like, oh, well, of course, if the coefficients of x are relatively prime and the coefficients of g are relatively prime, then when we multiply f of x times g of x, then the coefficients of that have to be relatively prime. But I claim this is not totally straightforward. I mean, it's not. It is true, but it's not something that just jumps out as being obviously true. So just to give an example, why don't we take f of x to be, let's say, 3x cubed plus 9x squared minus 11x plus 6. All right, so that's primitive because it looks like some of these coefficients have a factor of 3 in common, but 11 doesn't have that. And there's no other prime factor that the four coefficients have in common. So that's primitive. And g of x, let's let g of x equal, let's say, 6x to the fourth minus 17x squared plus 3x plus 12. All right, so those are two polynomials. They're both primitive. It looks like an awful lot of the coefficients have 3 in them, not that one, but this one does. This one has a factor of 3, and so does this, and so does this. And the thing I want to illustrate here is that even though there's a lot of 3's, there's a term of f of x that fails to have 1, and there's a term of g of x that fails to have 1. And that's going to lead us to a point where we will find a coefficient of f of x times g of x that does not have a factor of 3. And then other factors we'll have to deal with. But for now, we're going to focus on factors of 3. All right. For this theorem, it's going to be really useful, actually, to think of polynomial multiplication in terms of the array model. That array model is useful in school, but it's also useful for us. It's useful for thinking about just the structure of how polynomial multiplication works. So what I'm going to do is I'm going to put f of x over here on this side of the box, g of x up here, and I'm going to try and get this split into a 4 by 5 array. Let's see if I'm successful. Okay, that's not half bad. And then 1, 2, 3, 4, and 5. Not bad for a day's work. Okay, so f of x is going to be 3x cubed plus 9x squared minus 11x plus 6. And I left 5 boxes or 5 cells on the g of x side because I have a 4th degree polynomial and one of the terms just happens to be 0. But I'd like to include that in the analysis. So 6x to the 4th. And then this one's 0. 0x cubed, just for record keeping there. Negative 17x squared. It's negative 17. Plus 3x plus 12. And now we're going to start filling in partial products in this box. Like this, for example, is going to be negative 17x squared times 3x cubed. I realize, though, that you did not log into YouTube so that you could watch me do polynomial multiplication for 5 minutes. So I'm just going to pause the video and then fill in the partial products. I will show one just to show what it is we are doing. This one is negative 51 x to the 5th. And let's just do one more. This one here in the second row, 4th column, is plus 27 x cubed. Okay, I'm going to pause and do the rest. And there we have it. Okay, I hope that I didn't make any multiplication mistakes. I gave myself kind of a difficult task with this 11 times 17, but I think I've got all of the products correct. All right, now our goal in looking at this was to think about just the fact that so many of the coefficients of f and of g are divisible by 3. It seems like it could be possible that the product, everything ends up being divisible by 3, even though there are some outliers here that aren't. And I'm going to show that that's actually not going to happen. In other words, we're going to show that there is a coefficient, at least one coefficient of the product that ends up not being divisible by 3. And then other possible prime factors we'll deal with later because they're all going to fall under the same proof. But we prove this theorem about f of x times g of x being primitive. We prove it one potential prime factor at a time. That's why we're focusing on 3 right now in our example. Okay, let's see if our highlighter tool works. I've never tried this before, so it should be interesting. Yeah, let's try that thickness, and then we'll use yellow. Let's see if, oh, that's cool. Okay, so it does highlight. All right, that's great. So anyway, the thing I want to focus on here is if you look inside this array, it looks like most of the coefficients in the product, or at least most of these partial products, do still end up being divisible by 3. I want to focus on the ones that aren't. Okay, so one thing that we know is that this coefficient right here, 6 on 6x to the 4th, that's divisible by 3. So any partial product involving it is going to be divisible by 3. So I know, for example, that this coefficient, this coefficient, this coefficient, and this one, all are going to be divisible by 3. All right, same here with 0. Well, every coefficient in this column ends up being 0. That's even better than being divisible by 3. And then in the third column, I don't know, I've got a negative 17 there. That's not divisible by 3, so I can't make the same inference. But this plus 3x, that's divisible by 3. So everything here is going to be, let's see, change the thickness on that. There we go. Everything here is going to be divisible by 3. Sorry, I'm getting a little confused between which tool is which in my app here. And then 12 is divisible by 3, so all of these also are divisible by 3. All right, so that we know so far. Everything in the yellow boxes is going to be divisible by 3. Now, what's going to happen when we combine like terms with the same power of x? I don't know. We're going to deal with that in just a bit. But now let's look at the coefficients of f of x and figure out which of those are divisible by 3, and then which partial product that's going to force to be divisible by 3. All right, so I'm going to put the thickness back here, and then let's use a different color this time. Let's use, how about pink? Okay, so for example, 3x cubed divisible by 3. So everything in that row is going to be divisible by 3. So this one, this one, this one, this one, and this one. I apologize for the conflicting colors. I hope that you're able to see both the yellow and the pink. 9x squared divisible by 3. So everything in this row, boom, 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 boom. Negative 11 is not, so we'll skip that, but plus 6 is divisible by 3, so these are all divisible. And now, take a look at this. I have only one coefficient left that was not divisible by 3. And it's not divisible. I mean, not only did I not rule it out, but if I look at negative 11 times negative 17, neither one of those is divisible by 3. So I know their product won't be divisible by 3. Now, you may be saying, well, okay, you have a 187x cubed, but that's not a term of the product polynomial. The product polynomial has a whole bunch of x cubes that we got to add together. It's got this one, and it's got this one, and it's got this one, and this one. But then I say, well, wait a minute. All three of these, this one, and this one, they're all divisible by 3. So if I have a single one here that is not divisible by 3, then the sum won't be. And I can verify that by actually adding these together. So the x cubed term of the product, I'm just going to add along this diagonal. That's going to be 0x cubed plus 187 x cubed plus 27x cubed plus 36x cubed. 27 plus 36 is 63. 63 plus 187 is a nice, cool 250. So my x cubed term of f of x times g of x, that's the cubic term of f of x times g of x, and that cubic term is not divisible by 3. Sorry, that exclamation mark there means exclamation, not factorial. Although I guess it's also not divisible by 3 factorial. So anyway, that means that my f of x times g of x has at least one term that is not divisible by 3. So that's great. So now I've established that for 3. The way that this theorem is going to go, the way that the proof is going to go, and we're going to do the proof in the next video, is we're going to show that there is no prime by which every coefficient of f of x times g of x is divisible. In other words, if I look at a specific prime and focus on that prime, I will always find at least this one little term out here that is not divisible by that prime. That's how the proof will work. At this point, I want to invite you to see if you can generalize this argument, because we are going to give the proof in the next video. But before you look at that video, see if you can figure out how you would write this up in general. Because what we see here in this box, this idea that we can look at coefficients not divisible by p to find a potential coefficient of the product not divisible by p, that's the entire reasoning of the proof. Writing up the proof is a matter of just generalizing that and figuring out how to structure the argument around this idea of looking at one prime at a time. So I would like for you to think about how to prove that before watching the next video, but I'll see you there.